G'day guys, it's Dr. Budnanyakara, respiratory and sleep physician, and today we're going to explore some principles of gas exchange and eventually derive the alveolar equation. Okay, so let's start with a pictorial representation of the lung. Apologies for my poor diagrams. Okay, so there's the lung and there's the circulation. Okay, let's zoom out a bit more. All right, so remember that carbon dioxide is produced by substrate metabolism. So substrate being either carbohydrates, fats, or amino acids. It gets metabolized through aerobic respiration to produce carbon dioxide and water, and remember, a lot of energy in the form of ATP. Let's call carbon dioxide production in mils per minute, so V dot CO2, which is expressed in mils per minute, is carbon dioxide production. And oxygen consumption is V dot O2, again in units of mils per minute, which is equal to oxygen consumption. Okay, and remember our respiratory quotient was simply V dot CO2 over V dot O2, the ratio of carbon dioxide produced to the oxygen consumed. And remember, for pure glucose, remember the equation that was C6H12O6 plus 6 moles of oxygen consumed for every 6 moles of carbon dioxide produced, and water, and remember that generated 36 ATP molecules. And so the respiratory quotient using glucose as a fuel was 6 per 6, which equals to 1. Alright, and it's different for fats. For pure fats, we're looking at ratios of about 0.7. And for a normal human diet, which consists of a mixture of fats, proteins, and carbohydrates, our respiratory quotient is estimated to be about 0.8. Now we'll come across the importance of this. Another principle I want to illustrate is steady state. Now in steady state, what this means is the body is in a state whereby what is produced is equal to what is eliminated. So the amount of carbon dioxide produced is equal to the amount of carbon dioxide eliminated. Now, where does carbon dioxide get eliminated? Well, it gets eliminated in the lungs. We breathe out carbon dioxide. So, if we go back to our diagram of the lungs, all the carbon dioxide produced here by tissue metabolism through the process of aerobic respiration and other forms of metabolism will diffuse down its concentration into the alveoli, where it exerts a partial pressure, which is eventually breathed out. And what gets breathed out? Well, simply that's the amount of volume ventilated, which is in mils per minute. So we call that the alveolar ventilation times the amount of carbon dioxide as a fraction of that air, which we'll call that FaCO2, the fraction of carbon dioxide that gas occupies. Okay, so let's go to let's just go down here. So we know that if we know that the amount of carbon dioxide produced is equal to how much is eliminated or breathed out, then we know that V dot CO2 equals to the amount of alveolar ventilation, which we'll call V dot A, times the fraction of carbon dioxide that occupies that volume. We say FaCO2. Now remember Dalton's law in that the atmospheric pressure, or whatever pressure is within a container, is simply the sum of the individual fractions of the component. So FaCO2 is simply the partial pressure of carbon dioxide in that alveolus divided by the total partial pressure, the total pressure within the alveolus. So if we input this equation into here, then we see that the amount of carbon dioxide produced, or V dot CO2 in mils per minute, equals to the alveolar ventilation, essentially what we're breathing per minute in mils per minute, times PaCO2, which is the alveolar partial pressure of carbon dioxide, divided by the total pressure within the alveolar. So if we rearrange it and solve for this variable here, therefore the amount of carbon dioxide in the alveolus as expressed by partial pressure equals to the amount of carbon dioxide produced divided by the alveolar ventilation times the pressure within the alveolus. Now if we express this in standard temperature and pressure and express this as a constant, then we get what we know as the carbon dioxide equation, which is the big A CO2 equals to carbon dioxide produced via V dot CO2 divided by V dot A, which is alveolar ventilation, times 8.63, which is a constant. Now remember that the gas exchange membrane is very small. It's very, very thin, less than 2 microns. So the arterial CO2 is essentially equal to the alveolar CO2. There's complete equilibration. The carbon dioxide that's within the blood, remember it's dissolved, it's in the form of carbaminohemoglobin, as well as carried in bicarbonate, completely equilibrates with the alveolus due to the lack of diffusion limitation. So this gives us one of the equations. PaCO2, essentially substituting this equation here, equals to V dot CO2 upon V dot A, or big A, sorry, times a constant, 8.63, which is the pressure within the alveoli expressed in standard temperature and pressure. So what does this show? Well, it shows that the arterial carbon dioxide is related directly to the carbon dioxide production. And that kind of makes sense. If you're producing more carbon dioxide through metabolism, say for example you're in a catabolic state, then your carbon dioxide production where your arterial carbon dioxide level will increase. Also, if you think about it, if your alveolar ventilation increased, so the amount of gas that you're breathing out per unit time per minute increases, then the amount of carbon dioxide that you're breathing out is also going to increase. So the amount of carbon dioxide as measured by partial pressure of carbon dioxide in the arterial gas is going to drop. And we can model this with the following graph. So if we draw PA CO2 here with respect to alveolar ventilation, we can see that this is going to be a hyperbolic curve. So for very low alveolar ventilation, our carbon dioxide is going to be high. And for very high alveolar ventilations, our carbon dioxide level is going to be low. Now, that's at a set carbon dioxide production. But if we increase our carbon dioxide production, this curve is essentially going to be shifted as follows. So for every unit of alveolar ventilation, the amount of carbon dioxide is higher. So if we are producing more carbon dioxide, then to have the same value of PaCO2, we're going to have to increase our alveolar ventilation. Okay, I hope that makes sense. So let's do the same analysis, but with oxygen. So we'll draw the lung again. Again, many apologies. We assume steady state conditions in which the oxygen consumed is equivalent to the oxygen that enters the system. So oxygen consumption, or V.O2, is essentially equal to the oxygen entering the system, which is how much is breathed in minus how much is breathed out. Because if you think about it, whatever's breathed in, and then if the rest is breathed out, must have entered into the pulmonary circulation for oxygen consumption by the mitochondria in aerobic respiration. So V.O2 then, let's have a look at each of the sides. So what comes in is simply the amount of air that we breathe in, which we'll say V.A, which is, remember, ventilation times the amount of oxygen in that air, and what we breathe out is again the ventilation, V.A, times what's within the alveoli, which is the fraction of air and that within the alveoli that's occupied by oxygen, which is FaO2. Therefore, V.O2 is simply the difference between what goes in and what comes out, because that must have gone into the pulmonary circulation for oxygen consumption. So we get V.O2 equals to V.A FiO2 minus V.A FaO2. Now if I take this over here and we simplify that, then we know that oxygen consumption equals to V.A, the fraction of gas that's inspired, that's oxygen, minus the fraction of gas within the alveoli, that is oxygen, FaO2. Now, if we express FaO2 as a function of partial pressures, then it should make sense that this equation boils down to this. V.A FiO2 minus the alveolar partial pressure of oxygen, P big AO2, upon the actual pressure in totality within the alveolus, PA. All right. Now remember what VCO2 was. VCO2 was simply the amount of alveolar ventilation times the fraction, the partial pressure of carbon dioxide within the alveolus, and that'll be little a, CO2, assuming complete equilibration, over what's within the pressure of air within the pressure of gas within the alveolus. Now remember what R was. R was equal to V dot CO2 upon V dot O2. Remember, that was the definition of the respiratory quotient. So if we put equation 1 and equation 2 together, so if we divide equation 1 by, equation 2 by equation 1 to get VCO2 divided by VO2, which equals R, then we get the fact that R here equals to PA CO2 upon PA, big PA, times the alveolar ventilation upon big VA, FiO2 minus PaO2 upon PA. Now if we do some fancy mathematics, cancel this, we make it a common term, therefore we get R equals to the following: PaCO2 upon PA divided by FiO2 times PA minus PaO2 upon PA, and again doing some cancelling, for R equals to arterial partial pressure of carbon dioxide divided by FiO2 times the pressure within the alveolus, total pressure within the alveolus, minus the alveolar partial pressure of oxygen. Now what's the pressure within the alveolus? Well, the pressure within the alveolus is simply the barometric pressure, right, minus the water vapor pressure. Remember, that's where the gas occupies now. It's been fully saturated by water, so we need to account for that. So if we put this into here, then we get R equals to PaCO2 upon FiO2, barometric pressure minus the water vapor pressure. Remember, at 37 degrees, it's 47 millimeters of mercury, minus the alveolar partial pressure of oxygen. And if we take this over here and this over here, just using simple algebra, then we get this equation. Equals to PA arterial CO2 upon R. And therefore, if we further rearrange this to express it just in terms of the alveolar partial pressure of oxygen, we get this: PaO2 equals to FiO2 Pb minus P water minus PaCO2 upon R. And that is the alveolar partial pressure of oxygen within the alveolus. And I hope that makes sense. And that's how we derived it. Remember, we first figured out the equation for carbon dioxide. We then figured out the equation for oxygen using steady state principles. We then expressed it in terms of R, and then we solved it for the partial pressure of oxygen within the alveoli. All right, so if we look at this in more detail, we can see a couple of things. Well, just express it again so that it looks a bit more nicely. 1/2 PB minus P water minus PaCO2 over R. Okay, let's see what happens when we influence a couple of variables. So, if we increase the fraction of oxygen that we breathe in, then clearly you're going to increase this variable, and clearly you're going to increase this number. And that kind of makes sense. If you breathe in more oxygen molecules by increasing the fraction of oxygen, say you're adding supplemental oxygen, you're going to increase the partial pressure of oxygen in your lungs. What if we increase the carbon dioxide? So let's just say you reduce your alveolar ventilation and consequently your PaCO2 increases. Well, if your PaCO2 increases, this number here increases. If this number here increases, then we get a smaller number for the alveolar oxygen. And that kind of makes sense. If you think about it, if you're not ventilating enough, then the amount of carbon dioxide that accumulates in your alveolars is going to be high. So the carbon dioxide, the partial pressure of alveolar carbon dioxide is going to increase. Also, remember, you're not replenishing your alveolar oxygen by ventilation. So your alveolar partial pressure of oxygen is going to drop. I hope that kind of all makes sense. All right, well, thanks for tuning in, and I'll catch you another time.